Okay. But yeah, this week is supposed to be preparing for solo flights, and where objectives per the syllabus are understanding how and why weather forms, being able to predict weather and its effects on aircraft performance, knowing where to find proper weather information. That means not watching the Weather Channel, and reading and understanding weather charts. So there's a lot to do by the end of this week. A lot to learn on the Cessna training app. You're supposed to be on weather and weather briefings. I'm sure no one's following that, but if you need review, there's basically marking you here. So now I just have Mitch is gone. He told me that, so I've been marked virtual, not gone. He couldn't be here today. He let me know last week. And then Otto's still missing, so we got everybody else. He's not gone forever, as far as I know. He said he was going back. Okay, let's get into it. Yeah, as we go through this week and next week, at the beginning of class, let me know if you're doing the improve and control phase checks, if that's really happening for anybody, and then we can start probably next week getting into, yeah, next week looks like it's going to be a review focused on knowledge, or at least the pre-solo phase checks. So that'll be the first real one, I guess, that you're doing. It's going to be with a phase check instructor that's not your own instructor. So it'll be very much like a mock check ride, but it won't have all the information of a check ride. It will just be focused on these few topics that we've learned in the first weeks. Okay. All right, weather. This is weather theory today. So broad overview of weather, and there's a lot of words, way too many words on all these slides. So copy down what you need. I'm going to tell you what's important that you need to write in your notes, but there's a lot of words, so we'll get into it. Weather is important for flying, right? It influences our performance, obviously. Big overlying understanding of weather theory that we have to know is weather is always caused by heat exchange. Bold that, highlight it, whatever you need to do in your notes. Weather is caused by a heat exchange. That's our big overlying idea today. And then the rest of this is self-explanatory. The state of the atmosphere at a given time, such as temperature and moisture and wind and visibility and pressure, all have influence on aircraft performance and flying safety, but weather is always caused by and accompanied by a heat exchange. So where are we getting, what's the, yeah. Everyone was shivering when we got in here, so I turned it off. Actually, can you there we go. There's some sort of halfway fan, so we're not awful, like it's some air. Okay, back to heat exchange. What is our source of heat? The sun. The sun. Thank you. The sun is our source of heat, so that's going to be causing how weather is created. It's going to be causing wind pattern, circulation of air, all of that. So let's talk about the atmosphere. The atmosphere is a big blanket of air that covers the earth, and inside the blanket of air is all different types of gases, and they're all constantly moving. So the movement of gas, just like a fluid, like we talked about air as a fluid, the mixture of gases is in constant motion, and this is what is creating weather based on the heating of the earth from the sun. So we'll start with, you could write down it's almost 350 miles from the surface of the earth, but it's mainly a mixture of gases that surrounds the earth, that is like a fluid and it's in constant motion. So the composition of the atmosphere is about 78% nitrogen and 21% oxygen. And then the rest of it is like trace gases. So you don't need to know the trace gases, argon, carbon dioxide, other trace gases. Main thing we want to know is it's mostly nitrogen and 20-ish% of oxygen that makes up our atmosphere. Those are our main gases. Okay, we got this. We're still right. We keep moving. Layers of the atmosphere. So most important ones we want to know are the troposphere and the stratosphere. And what's not in this picture is a boundary layer between the troposphere and the stratosphere that's called the tropopause. Also spelled TROPO pause, PAUSE, I believe. There's a slide on here that's called the tropopause that we'll get to. But troposphere we'll start with because that's the most important. The first layer, I'll go to the next slide that has exactly the dimensions of it, but the troposphere is important because this is where the vast majority of weather is concentrated. Weather, clouds, storms, temperature variances, they're all inside the troposphere. And we have, I'll go to the next slide so you can write this stuff down if you want to, but inside the troposphere, we have an average temperature decrease, which is called the average lapse rate. So for every 1,000 feet of altitude, 2 degrees of Celsius is decreased. This is going to be called, we'll get to a specific slide later on, but this is called the standard lapse rate. I'm going to repeat it again because you are going to have to write it down at some point. Every 1,000 feet of altitude decreases in 2 degrees Celsius. So we're decreasing temperature as we increase altitude. And then they also have an average pressure decrease at a rate of about 1 inch, this inches of mercury, 1 inch of mercury per 1,000 feet of altitude gain. So you're decreasing both temperature and pressure as you increase altitude by 1,000 feet, and that's decreasing 2 degrees Celsius and decreasing 1 inch of mercury. Okay. We keep going. Here's the tropopause that I didn't have on the picture. This is like a boundary layer at the top of the troposphere that kind of encapsulates all of the weather in the troposphere. Most of the weather. It's not 100%. There's still some moisture that escapes out, but it keeps pretty much all of the moisture and the weather in the troposphere. So this is like a boundary layer before you get to the stratosphere. Okay. It varies with latitude within the season. It has an elliptical shape as opposed to a round shape because we're a sphere, and that means at the equator we have a greater circumference than at the top of the Earth. And the location of the tropopause is important because it's associated with the jet streams. Okay, we know what a jet stream is, the fast-moving circulatory air. Jets get into the jet stream to go faster. It pushes them faster along their route. And we'll talk about what the jet stream has to do with cloud formations, but just as a note right now, write down that the location of the tropopause is associated with the locations of jet streams. There's a couple on the Earth. And then the temperature in the tropopause remains fairly constant, even with changing altitude, which is different than the troposphere that we just talked about. Because the troposphere, as we increase in altitude, decreases by what? 2 degrees Celsius. Thank you. And what is that called? Lapse rate. Thank you. Okay, we know what we're talking about. Let's move on. Above, did they just skip the stratosphere? Apparently. Thermosphere? Yeah, they just skipped the stratosphere. Here's a slide on the mesosphere. Located 31 to 50 miles above Earth's surface. It still gets progressively colder with altitude as we're increasing altitude. The top of this layer is the coldest place found within Earth's system. So minus 85 degrees Celsius, 120 Fahrenheit. What's important to know about the mesosphere is there is barely any water vapor present. So barely any water vapor means basically no clouds. There's a type of cloud on here. I don't even know how to pronounce that out loud, but other than this certain type of cloud, I can't even say that. But instead of that cloud, there's no other clouds because water vapor, moisture is needed to form clouds, right? So at the top of the mesosphere, there's very scarce water vapor present. So very scarce on clouds. Since there is still a little bit of water vapor, these are going to be the highest formed clouds in the Earth's atmosphere. Let's keep moving. Thermosphere, even higher. So what they're missing on the slide is that second bullet point. They forgot the word temperature. So an increase in temperature with altitude. So this is going backwards from all the other layers. We're decreasing in temperature as we get higher in the atmosphere. And then the thermosphere, we're actually increasing temperature with altitude due to the very low density of molecules up there. It's cloud and water vapor free. So the mesosphere has very limited water vapor, so that's where the highest clouds are, but it still has water vapor, so clouds are still able to form. The thermosphere, there's no water vapor, so that means there's no clouds. Pretty straightforward. This is where you might see the aurora borealis, up in the thermosphere. This is also where the space station orbits. So unless you become an astronaut, we won't be getting anywhere near the thermosphere. We got this. Biggest points are it increases temperature with altitude, which is different than what we've talked about for the rest of them. And it's cloud and water vapor free. Got it?
The temperature goes up.
Yeah, that's what they're missing on the slide. It's supposed to say increase of temperature with altitude because of the very low density of molecules found there. Yeah, on the slide, it just says increase with altitude. They're talking about temperature. All right. Okay, here's the meat of what we're talking about today. Circulation patterns around the Earth. So when we're talking about a heat exchange is the cause of all weather, the heat exchange is causing circulation patterns around the Earth. So we'll start with warm air rises, right? Because the heat causes the air molecules to spread. So we know maybe from science class that when you heat like a parcel of air, you heat something, the molecules start to vibrate and move around. And as they start to vibrate, that's what's spreading them apart, okay? So warm air, once you heat the air, the molecules start to move around. Moving around causes them to spread out. Spreading farther apart means that parcel of air, when they talk about density and stuff, we're talking about, a specific, parcel of air, just like one section of air. So when we warm up that section, the heat causes the air molecules to move and spread apart. Spreading the air molecules apart means that the whole parcel of air itself becomes less dense, right? And less dense is how the air rises, okay? So it's expanding from the heat and then becomes less dense, and that makes it lighter than surrounding air. And that's what causes warm air to rise. Are we following this part? Okay. I'm talking about the density of air in relation to the temperature and the heating of air. So we'll go to cooling. As air cools, those molecules come back together and pack together closely. Packing those molecules together makes it more dense than the surrounding air, which makes it sink. Are we following? Yes, everyone's just kind of writing, some nods, okay? We're talking about density of air in relation to temperature. So we heat up the air, the molecules move around, they spread out. Spreading out means less dense air, means it's expanding, becoming less dense. Makes it lighter than surrounding air, so that air moves upward, rises. Then opposite, as air cools, those molecules are coming back together, packing together closely. Since they're packed together closely, that's creating a denser area. That dense area thus sinks because it's more dense. So sinking cool air, rising hot air. Are we understanding that? And we're seeing with my hand movements, rising air, sinking air creates a circulation pattern, right? Because that cold air, that cold dense air is going to move in to fill in the rising air that has just gone up. Okay. I think that's covering all of the points on here. As a result, cool, heavy air tends to sink and replace the warmer rising air, which creates a circular pattern of motion in the atmosphere where air is rising after it's being heated and then cooling. And as it cools, it sinks back down and replaces the area where that warm air just rose. Does that make sense? It's creating a circle of air, up, down, up, down, up, down. Rising, falling air, heating up, cooling down. Got it? Okay. They also have in here solar heating causes higher temperatures at the equator, which causes air to be less dense and rise. Okay? Does that make sense? The hottest areas where air is being heated the most is around the equator because the equator is closer to the sun, right? Because we're a sphere. So those areas around the equator are the closest to the sun. They're being heated the most. That means they have the most warm rising air. That air is going to be less dense and rise from areas of the equator. So that area at the equator, that warm air is going to flow towards the poles and become more dense and sink back towards the surface. So from the equator, if where are the pictures in here? I have some pictures. Let's look at, oh my god, you can't even see it on my, okay. Surfaces, detail. Okay, this is getting a little farther than the slides do, and I don't even think the slides cover that today. But this circulation pattern is how all air circulates around the earth, and they put into cells, 3 different types, Hadley, Ferrel, and polar cells. I'll see this right. Okay. So the Hadley cells right next to the equator, you can see the red arrows. That's the rising air from the equator, rising up from the equator, that hot air. And then as it moves back north towards the North Pole, it starts to cool and then fall back and then move back to the hot air rising. And that's how you have the pattern of the Hadley cell right next to it. Then you have the polar cell up at the top that has colder air that moves down towards the equator and back. And then the ferrule cell in the middle is actually moving based off the other two cells that surround it. Just getting a little too far. We'll get to this later on the week, but the point is, around the equator, higher temperatures, that means that air is going to rise at the equator and then start moving north towards the pole. And most of today's class, we're just going to talk about the northern hemisphere because that's where we're flying in. Southern hemisphere is going to be opposite to all of this, but does everyone understand the equator just to begin with? You don't have to understand the cells right now, but just the equator, how it flows towards the poles, it cools down and then sinks back to the surface and then back to the equator. So it's moving like this from, if the equator is here, it's moving like this around. Okay, we're gonna keep going. We need to get to all of these, but stability. For atmospheric stability, this is the most important part that you need to write down and highlight. Stability of the atmosphere depends on its ability to resist vertical motion. Stability equals ability to resist vertical motion. Okay? So a stable atmosphere means that vertical movement is difficult, and an unstable atmosphere means vertical movements tend to be larger, and that results in convective activity and turbulent airflow. Okay? So that's exactly what they're saying. Instability leads to turbulence, excessive vertical clouds, severe weather, all that. So basic idea, stable atmosphere resists vertical movement. Unstable atmosphere has large vertical movement. Okay. Rising air expands and cools due to the decrease in air pressure as altitude increases. So we know the air pressure is decreasing as we increase in altitude. Rising air is expanding and then cooling also due to the decrease in pressure. Okay. And the opposite is true for descending air. Atmospheric pressure increases, the temperature of descending air increases as it's compressed. We'll come back to this. Hopefully, okay, there's some pictures and fun. Okay, looking, can I zoom in? All right, you should have in King's School seen a table of things that unstable and stable air is known for. So unstable has a certain type of cloud, stable air has a certain type of cloud. It's talking about precipitation, smooth air versus turbulence, and good visibility and poor visibility. Okay, so rising air with vertical motion creates these fluffy clouds. What are these clouds generally for unstable air? Cumulus. Nimbus is adding the water into it. So cumulus is going to be these tall, fluffy clouds. That vertical motion is being created. That hot air is rising. And then we have the little flatter clouds like this. This is going to be with stable air. What are those clouds called? Stratiform clouds. Okay. So 2 types of clouds. You're going to be asked this a bunch in the phase checks and the check ride about what are characteristics of a stable atmosphere versus an unstable atmosphere. So you need to know this little box and be able to explain. So you need to know unstable air is associated with cumuliform clouds. Those are those big, fluffy, vertically developed clouds. And then stratus or stratiform clouds are really thin. I'm gonna pull up maybe a picture they have later, hopefully. There's way too many words in this, but because that air is more dense and sinking, that creates a flatter, less vertically developed cloud. That's gonna be the stratoform or the stratus clouds, okay? And then we already talked about unstable air is rough air, it's creating turbulence. Stable air is smooth air. Precipitation for unstable air is showery. And then stable air can have continuous precipitation. Some people get this confused a lot when talking about stable or unstable, or they think continuous precipitation means unstable, but unstable would be like scattered showers, right? Stable air is continuous precipitation. And then good visibility versus poor visibility. Unstable air can have good visibility because that vertical motion is moving things out of the way, as opposed to stable air kind of keeps clouds and fog in place, which creates poor visibility. Does that make sense? If you have a lot of vertical motion and rising air, you're able to move clouds and fog out of the way for good visibility. If you have stable air, it's keeping those clouds and fog where they are, and clouds and fog create poor visibility, right? Okay. Do we have this chart down? Good. Okay, let's move. Okay. The adiabatic process. So this again is a lot of words. Did I write them? Edit. Let's see markup or drop. But out of this, you want to write down. Okay, we already talked about the standard lapse rate, right? So that's going to be as air ascends through the atmosphere, the average rate of temperature change is 2 degrees Celsius per 1,000 feet. This has to do with moist air versus dry air. So at the very bottom, it has the dry adiabatic lapse rate, unsaturated air versus the moist lapse rate. Write those two down. We have the dry lapse rate is 3 degrees Celsius per 1,000 feet, and the moist lapse rate is basically 1 to 3. It's 1.1 to 2.8, but you could just write between 1 and 3 per 1,000 feet. Okay. So this has to do with water vapor in the air. Water vapor is lighter than air. So as moisture decreases air density, it causes it to rise. So if there's more moisture in the air, that's taking up more space of the water molecules is taking up more space where the air molecules are, right? So that's expanding. And we know expanding creates less dense air. And as moisture decreases, those water molecules are coming out of the air, it becomes dense again and it sinks. Does that make sense? Water vapor is lighter than air. It's creating water molecules or taking up space where air molecules would be. Are we following? Are we writing this down? Everyone seems to be writing. We already talked about the top, about the rate at which temperature decreases with an increase in altitude is called its lapse rate. So its standard lapse rate is 2 degrees Celsius per 1,000 feet, but it changes. We also have a dry and a moist lapse rate because water vapor is lighter than air and thus decreases air density, causing it to rise. Okay. I'm gonna keep moving. Feel free to go back to the slides if you need to. Okay, pressure. Atmospheric pressure. The unequal heating of the earth, which causes all weather, not only changes air density, but creates circulation patterns, like we talked about. So it also changes air pressure, or the force exerted by the weight of air molecules. So air molecules have a weight to them, like we just talked about. An air molecule is heavier than a water molecule. So they have weight, they take up space, even though they're invisible. So the pressure at any given time and place differs. I mean, that's given. The pressure differs with altitude, with temperature, and with density of air. And we talked about how pressure can increase, or atmospheric pressure can affect performance, especially takeoff, rate of climb, and landings. So what is the pressure, atmospheric pressure? What specifically are we talking about with types of density? We remember talking about density, altitude, yeah. And we have density, altitude has 3 H's that affect it, right? Do we remember what 3 H's are? Nobody? Go.
The heat, humidity, and height.
Yes. Heat, humidity, and height, which we're talking about here. Heat, temperature, height, altitude, and density of the air with humidity. Because humidity is going to be that added moisture to the air, right? That added water molecules to the air. So this is just talking about these conditions affect takeoff, rate of climb, landing, performance. Let's keep going. Standard atmospheric pressure. We've already went over this, but there's also a standard temperature of the atmosphere. So standard sea level pressure is 29902, and this is inches of mercury. Little 2 commas, that's inches of mercury. And then standard temperature is 59 degrees Fahrenheit and or 15 degrees Celsius. If you don't have this memorized, write it down. This is going to be important in performance calculations. You need to know the standard temperature and the standard pressure. You can also remember standard atmospheric pressure in millibars. That's going to be 1013.2 millibars, 1013.2, right there on the 3rd little arrow. So pressure is reported usually in inches of mercury, like 29902, but it's also millibars that you might need to know is 1013.2. And then we already know as altitude increases, atmospheric pressure decreases. Or we should know that already. Because we already talked about the average increase of every 1,000 feet of altitude, you're decreasing about 1 inch of mercury. Okay. Again, I realize this is a million words and there's barely any pictures to this, but we'll get back to all of this. We just need to take notes first, get all of the information, and then we'll move back to explaining this. Okay. As pressure decreases, density altitude increases. That has an effect on aircraft performance. That's when we're talking about how height, one of the H's, altitude, as when we're talking about height, altitude affects density altitude because as pressure decreases, so the higher you go in altitude, the less pressure there is, and with less pressure, density altitude increases. Still writing. Okay. Pressure systems. Here's where we're gonna have to wake up and lock in on this stuff. Everything else is just stuff you need to write down in your notes to learn, memorize later with the standard pressure and temperature and stuff like that. Pressure systems is part of reading charts and knowing what's going on. So we already talked about the atmosphere is a lot of different gases all stacked together, and those gases exert pressure. So I guess fun fact on here is that the layers of gas in the atmosphere exert nearly 15 pounds of pressure on your body at all times. And the amount of pressure in any given location is not the same. So air pressure varies on where you are, but this results in high and low pressure systems. So I'm sure we've seen this in King School or on the Weather Channel or whatever there is, but they have red and blue H's and L's on like a map of the US, and those are high and low pressure systems, and they impact the weather in the region. Okay, so this is just an overview. We'll get into each one. So I wish I could go to AW stuff. This is one of your approved weather resources. If you want to go ahead and bookmark this website, it's aviationweather.gov. This is where you're going to find all of your charts to look at. It's a bit of prog. Okay, everyone see the blue H's and the red L's everywhere across the US. Right now, we're talking about low pressure systems, so that's going to be all these red L's. Okay. To show you a picture, but I'll get back to the words now. So low pressure areas are red L's. The low pressure system has a lower density than the surrounding regions. So how they're going to talk about the higher density air around the low pressure system moves into the lower pressure area, and it results in like a suction into the low pressure area, which creates a circular pattern around the pressure system. So it doesn't even have it on here, but I want to be able to draw on something. Where's my pen? I don't think so. Do they have they don't even have a picture on here. So I'll move back so you can write down the words if you want to. But from the King School, does anyone know which way a low pressure system circulates or rotates? Is it clockwise or counterclockwise? Low pressure system.
Upward at count.
Counterclockwise. So this what you're gonna have to remember to talk about low and high pressure systems is how they move. So low pressure systems move counterclockwise and they move upwards and inwards, like Tiffany just said. So the way I remember this, if everyone can look up here for a minute, is screwing like a cap on and unscrewing. So unscrewing a cap is the low pressure system. So I'm moving my hand counterclockwise and I'm pulling up because I'm taking the top off of the lid or whatever. So if I'm taking the top off of a lid, or the lid off whatever, I'm unscrewing, so I'm going counterclockwise and I'm moving up. That's that upward, inward motion, counterclockwise. If I'm screwing something like a lid on, I'm moving counterclockwise and I'm pushing down and outward. Does that make sense? This is how you're going to remember how the low and high pressure systems move. So low pressure moves upward and inward and counterclockwise. High pressure moves clockwise. We're screwing the lid on and we're pushing down on the lid to screw it on. So it moves down and it moves out. Okay. I don't know where the slide on that is. It doesn't have it on here, but there's low pressure system if you want all the words on there. So low pressure system characteristics are undesirable weather. Why do we think that is? It's because of the movement that it's circulating, right? That upward movement that I just talked about, upward and inward, is creating vertical motion. Vertical motion is creating undesirable weather. Are we connecting that so far? Okay. You can also think of it as, if you know anything about hurricanes, they move counterclockwise, cyclonic. You can also hear high and low pressure systems talked about in cyclonic or anticyclonic. They're talking about that as cyclonic moves counterclockwise, and that's how hurricanes move. Hurricanes, like convective weather activity, moves counterclockwise, and that's called cyclonic. So if it's moving clockwise, like a high pressure system, that's called anticyclonic. Okay? Just so you're aware, because sometimes in check rides or face checks, or I'm not sure about the written how they refer to it, but if they call it cyclonic or anticyclonic, think about hurricanes. Hurricanes are cyclonic, and it's very, very bad weather. So it relates to a low pressure system that moves counterclockwise. Okay? Yeah, high winds, storms, hurricanes associated with low pressure systems. And it's all about the low pressure system has lower density than the surrounding air, and it's sucking in and upward, right? The air is moving counterclockwise and in and upward. So it's creating that vertical motion that's associated with bad weather. And it's pulling in the surrounding higher density areas into the lower pressure system, like creating like a suction effect, which rises in the middle. Okay? Does everyone understand the lid opening and closing? Does that make sense, everyone? Okay. That was the most helpful way to think about it when I learned it, so I'm trying to help you all out. Some people use a different method, but I think the lid makes the most sense. Some people call it the screwdriver idea too, if you're screwing, turning a screwdriver, tightening and untightening, but I think the lid makes sense because you're pulling the lid off and you're pulling it up. That's going to be that upward motion. It's coming inward and upward, and when you're screwing the lid on, you're pushing the lid down. That's that downward motion clockwise. Okay? We're gonna go move, that's the high pressure area. Is gonna be the blue H. Here's a sort of picture to show you what they do. So you see the high pressure area is moving clockwise and down. Low pressure is moving counterclockwise and up. High pressure areas are blue H's. That's where the low pressure system sucks air towards it. The high pressure system pushes air away from it into regions with lower air density. So air above these systems sinks down towards the center, and winds push it outwards, away from the pressure system. And like we talked about, high pressure systems generally have better weather, clearer skies. Okay? Do we have this written down?
Pressure reference, like two slides.
Yeah. Okay, there we go. Why do they put all the pictures together at the end? There we go. Warm air. They're like, here's how it actually looks on a prog chart. This is how the air is moving around a high pressure system. And you can see how the high pressure system, it's kind of moving away from that system. It's getting pushed down and outward. It has a bigger circle, whereas the low pressure system looks like it's getting tighter and tighter because it's pulling that air, sucking that air into the middle of the low pressure system. Does that make sense? Yeah.
What are those numbers associated with
Those are called isobars. We're going to talk about those when we get to reading charts.
Is that like the number that you gave earlier, the like 13 something?
Yes, they're in millibars. 1013.2 is the standard. Yeah, that's standard pressure. Isobars are lines of equal pressure around the area. So it's like It's like the equal pressure for that area, the number. And then standard is gonna be 10, 13.2 millibars, and all isobars are read in millibar units. So we'll talk about that. So like 10, I mean, if I want to get into it now, 1013 is the standard, right? So all these are closer to higher with 1013, as these are all lower than standard, right? With the low pressure, it's down in the 900s versus 1012. Okay. We'll get into isobars when we actually read frog charts, because we have to go over fronts before that. I think that's tomorrow, but there we go. Okay. Next big idea we have to go over is the Coriolis force. So areas of low pressure exist over the equator. Higher pressure exists over the polar regions. Okay. Due to a temperature difference. Obviously, the polar regions are colder than the equator. We talked about the equator is heated more than the polar regions because it's closer to the sun, our source of heat. So the resulting low pressure allows the high pressure air at the poles to flow down towards the equator. So the Coriolis force is all about the rotation of the Earth. So we know the Earth rotates on its axis and it's spinning, it's rotating around the sun itself, but it's also spinning on its own on its axis. So the force created by the rotation of the Earth is what's creating the Coriolis force. And it's basically the air in the circulation patterns, the air is being deflected to the right in the northern hemisphere. So if we think about, I think there's a video that will explain it better, but I'll try to explain it with words before you watch the video. If we have a globe and we're looking down on the globe and it's spinning, if we're at the top of the globe, it's spinning around this way. If we throw a ball, in theory, if we throw a ball from the North Pole down towards the equator, it doesn't go in a straight line towards the equator. It gets deflected off to the right. Does that make sense, everyone? Because the Earth is spinning, rotating, if we were to throw a ball from the North Pole down to the equator, it wouldn't just fall down towards the equator, it would get deflected in a path, a curved path to the right. Does that make sense to everyone? And it goes to the right because if we're like on top of the pole and looking at how the Earth rotates, it's rotating to the right. It's not from the side. Does that make sense? So if we're holding the globe like this and we're looking down from the North Pole and we drop a ball from the North Pole that goes down towards the equator, instead of falling in a straight line, it will follow a curved path to the right. Okay? Air is deflected to the right in the northern hemisphere, and it's deflected to the left in the southern hemisphere. This goes back to, we don't really care about the southern hemisphere right now. We're flying in the United States. We're following FAA regulations. That's for the United States. So don't worry about the southern hemisphere. Focus on how air is deflected in the northern hemisphere. And due to the rotation of Earth, air is deflected to the right. Okay? I'm gonna try to see if this makes sense from the video. I haven't watched the video. Can't watch it. You watch one? Okay.
What's going on? Every time I do the ball straight, it seems to bend.
Hello? Oh, it's playing on here, but it's not playing on
And what's going on? Every time I throw the ball straight.
Can someone hit
it
the,
seems to
Joby, can you
bend
hit the
to
light?
side.
Thank you.
No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to. That curve is created by Coriolis. You may have heard that it makes water in the bath spiral down the drain a certain way, or that it determines the way the toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's great red spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It affects the paths of missiles and sniper shots. But how does it work? How does it create hurricanes? Right now, it seems like the ball's curved. But let's take a look at what's really happening. My friends have put together this little experiment using a sort of spinning seesaw version. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round, but you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1/5 deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's beaming from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of your frame of reference, then could other forces like gravity or electromagnetism also just be products of your frame of reference, of where we live in the universe or in the multiverse? For more on that, check out our video, Do We Live in the Multiverse? There's talking fish. And if you want to find out,
Something.
Okay, light please. Thank you. Okay. So we get the big picture, right? He's talking about the same thing. It's being deflected to the right from the North Pole to the equator because of the rotation of the Earth. Then we also want to talk about the friction between the surface and the atmosphere. Within 2,000 feet of the ground, you're going to have different winds because of the friction between the surface of the Earth. So this wind is diverted from its original path because of the frictional force of the surface of the ground. Yeah. At the end, wind direction at the surface varies from what the wind direction just 1,000 feet above the Earth. I think that makes sense. Okay, so we have surface winds within 2,000 feet of the ground. And we have the Coriolis force pushing air towards or deflecting air to the right because we're rotating. Then we watched that video. So back, in case you haven't written it down already, they really want you to know you have to know this by memory. In case you haven't written it down, they have also given you the standard temperature and atmospheric pressure again. But at this point, I think I've gone over it 3 different times. So 2 degrees Celsius per 1,000 feet. Decreasing. Pressure decreases by 1 inch of mercury per 1,000 feet of altitude. Okay, I'm gonna assume everyone already got that. More words. Once we get through the next like couple slides, we're gonna take a break because even I'm like barely keeping my eyes open at this. Okay, wind currents or wind and currents. So we already talked about with Bernoulli's principle and the idea of lift that areas of high pressure want to go to low pressure. They seek out areas of low pressure. That's what we're talking about here. Air flows from high or areas of high pressure into areas of low pressure because it's always seeking out lower pressure. So in combination with pressure differences and the Coriolis force that we talked about, and friction and temperature differences, there's 2 kinds of atmospheric motion. There's convective currents, the upward and downward motion. In the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right. It produces a clockwise circulation around areas of high pressure. So the clockwise circulation that happens around high pressure systems is because of the deflection by the Coriolis force to the right. Okay? This is known as anticyclonic. I already talked about that. Anticyclonic, they're talking about cyclones move counterclockwise, hurricanes move counterclockwise. So anticyclonic circulation moves clockwise. I think we understand that. And the opposite is true of low pressure areas. Air flows towards low pressure and is deflected to create a counterclockwise or cyclonic. So they have that at the bottom. In case you didn't get it last time, high pressure clockwise, anticyclonic. Low pressure counterclockwise cyclonic. I think we got this. Yes.
There's a point about overflowing high pressure areas into low pressure. Like if they were to ask us about the net currents, then we just say the release principle with high pressure being above the airfoil and
You could use it to reference but it's basically just a constant in the atmosphere. Like it applies to Bernoulli's principle because we're creating that high and low pressure differential, but it's just it's just a known occurrence in the way pressure moves is it's always going to move from high pressure into low pressure. So it applies to Bernoulli's. That's how we heard about it first, but it's the same. It just applies to currents in this way in wind. High pressure is always seeking out low pressure. Okay. Then we talk about convective currents. This has to do with if you've ever been to Compton. And we're right in the middle of summer now. So if you've been over to Compton and you're on short final, maybe even a little bit at Torrance too, because we have a lot of buildings, but especially at Compton, and you're on short final to the runway and you get knocked up right before you cross over to like the displaced threshold, that's a part of convective currents. That's creating an updraft from the unequal heating of the ground. So over at Compton, the ground and rocks and buildings that are all right there are absorbing solar energy more quickly than like the trees and foliage and lakes and water and stuff absorb it slowly. So absorbing that heat fast is creating updrafts over buildings and rocks and sand and land like that, okay? So uneven heating of the air creates small areas of local circulation called convective currents. Causes bumpy, turbulent air experienced when flying at lower altitudes during warm weather. So during the summer, if you get close, you're flying closer to the ground, like you're on approach to a runway, you can get bumped up by turbulent air. We call them updrafts because of the unequal heating of the ground, right? The heating of the ground is creating that rising air that's knocking you up 100 feet or whatever it is, right over the runway, okay? Makes sense? The way that the ground is heating is creating a little current, a convective current, right over the ground. And that's causing an updraft that you sometimes hit right before you're on final for the runway. Okay. Mountainous areas. So we'll get into this more a little bit when we talk about, we'll start with mountain wind, and then this will be talked about more when we talk about the different kinds of fog and how they move. But with mountainous areas, the upside of the mountain, the air flows smoothly. It just flows right up to the top of the mountain, and then when it goes over top of the mountain to the other side, that's when it becomes turbulent. That's when it starts to break up and create turbulence on the other side. So smooth up the slope of the mountain, and then it falls over the top of the mountain and tumbles basically on the other side, creating turbulence. So that's what it's saying. Over the peak of the mountain, the wind on the leeward side is more turbulent and flows. Let's see if I can find a picture. This is, but it's important. Okay. Here's a pretty good picture. Wind flow over the peak of a mountain is smooth. It flows right up to the top of the mountain. And then as it goes over the peak to the other side, it creates this incredibly turbulent region of air that's moving in all different directions because it's kind of tumbling off the other side of the peak. It's really, really dangerous and important to talk about. I'm trying to see if there's another picture, but it's most important to talk about for us because on cross countries, there's a whole bunch of mountains, especially north of here. If you go towards Santa Barbara or you go all the way to San Luis Obispo or even more north, you're crossing pretty big mountain ranges, and you have to be especially careful around these mountain ranges because this picture that they're showing of like turbulent air looks, there's a good one. I think that's from the aim, but see how it's moving in every single direction off the top of the peak, but mostly they're all pointed back towards the mountain, right? That air is moving down and then circling back towards the mountain. That's going to be your plane. If you're on the other side of the mountain and you get caught in this mountain wind or turbulence, you're going to be pushed back into the side of the mountain. Really, really bad. Some people have lost thousands of feet of altitude flying on the back side of the mountain over the peak and gotten pushed not only back into the mountain, but they've lost, I think there's a story of someone that has lost 5,000 feet of altitude, which is, I'm surprised that they survived that. But it's very, very, very serious turbulence. You should be double checking the winds, how strong they are around the mountainous regions that you're flying at. And you should be extra cautious of where the wind is coming from and if it's flowing up the side of the mountain or if the wind is coming from the other side of the mountain and it's falling on you where you're flying. If you're flying on this side of the mountain and the wind is coming from the opposite side, that air is going to come right over the top of the mountain and push you down and into the mountain. and you're most likely crashing at that point. Okay? Understood. And this will get into talking about fog and stuff. There's upslope fog that moves up the mountain and stuff like that. Okay, there's more weather stuff, and I want to just keep going on the weather to get through it today so we can do the most with this week. Practicing how to read charts and unitars and stuff. So let's take a break for what is it? Come back at 10. Yeah, 10:20. And we'll keep going with this. If you need water or the bathroom or whatever who's talking, and we'll keep going and then figure out if you have any questions about what we've already talked about. Okay? 10:20.
Turn on the straw.
Next. Here. Yeah, we left it in that one, you know. This was the. Nothing. Oh, we can. I'm lining up to give you another for the line. And I found about three. Maybe. Five. Eight. Millions of years. So, yeah, it's. Like. You selling some into the South Park thing. It's some stuff in Southern School. It's good. Still kind of weird. That's it. Should make that the things with the popular. It's the same. You know, you might think they make it. It's inside to the it's never choose check.
Okay, 10:20, I'm starting again. No people are back. Wind shear. Wind shear is simply a sudden drastic change in wind speed and or direction over a very small area. So simply write down a sudden change in speed or direction of the wind, right? Wind shear is very dangerous. It can cause violent updrafts and downdrafts, as well as abrupt changes to horizontal movement of the aircraft. So it's either pushing you forward or back, depending on a headwind or a tailwind. So sudden change in wind speed and or direction is wind shear. Low level wind shear is especially hazardous because obviously you're close to the ground. So low level wind shear is associated with passing frontal systems and thunderstorms and temperature aversions, which we haven't talked about any of those yet. So we'll get to all of those about frontal systems and what causes or the ingredients of a thunderstorm, and then temperature aversions. Does anyone know what a temperature aversion is? Exactly. So we know normally the temperature is decreasing with altitude. So a temperature inversion is when the temperature is increasing with altitude, which happens a lot here. And I don't know, I haven't been up, it hasn't been too hot recently, but sometimes we get really bad temperature inversions in the area, and it gets like you'll get up to like 4,000 in the practice area, and it's at like 101 degrees, like up there. And that's not exaggerating. Maybe 100 is exaggerating, but if it's like 82 on the ground, you'll get up there and it's like 95. It's really annoying to practice in the practice area when it gets to almost 100 degrees in the air up there, but we have a lot of temperature aversions in the air, inversions in the area. So we'll talk about that, but that is one of the causes of low level wind shear. You'll also hear sometimes on approach back to the runway, tower will advise you of low level wind shear. If it's been experienced by other pilots, they will report that, and then it pretty much let everyone else know in the area when they come into land that low level wind shear has been reported. And this happens a lot on final, where you suddenly lose like 100 feet of altitude right over the runway, and that can be low level wind shear. And that if it does happen to you and you're by yourself, you should report it to the tower once you've landed, or your CFI will report it to tower so they can let other aircraft know that that's happening over the runway. So that's pretty dangerous on approach. Okay. We have another video. Yay. Yeah. Okay, hit the likes, please.
We're not getting any bad warnings from the weather or from other pilots, which we rely on as they come through it.
As the pilots at Delta 191 prepare for landing, rain begins to fall harder. At the foot of the runway, one of the most ferocious types of storm cloud stands in the way.
Floor landing check. Landing gear.
Down 3 green.
At the time, the type of storm the Delta crew is approaching barely has a name. John McCarthy is one of the world's leading experts on these storms.
It is a tiny thing, meteorologically speaking, compared to a big storm or a snowstorm or a hurricane. It's just like a needle in a haystack.
The needle is a microburst, one of the deadliest and at the time most poorly understood weather phenomena. They've taken down airliners before, but as Delta 191 makes its approach, there are no warning systems that can effectively alert the pilots of the danger they're in.
Prior to 1985, the radars on board the aircraft were built to detect thunderstorms, essentially heavy areas of precipitation. They were not effective. They were not even designed to detect the microburst.
If you're at the kitchen sink and you turn on the water and it goes straight down and it splashes out in all directions. And that's kind of what a microburst is, except that it is extremely bad news if you're an airplane flying through it.
When a plane hits a microburst, it encounters a complex and powerful set of conditions. Downdrafts and tailwinds batter a plane. It's a deadly combination. Just short of the runway, Delta 191 flies into the microburst.
We lose it. There it is.
Pilots at Delta Flight 191 did their very best to recover from this situation, and it didn't work out.
I must have caught sight of him just at the last millisecond, and he cartwheeled into the tank in just an instant, and then, of course, there was fire, not a ball of fire, but a wall of fire.
Just 27 people survived the crash of Delta 191. 137 people are killed. After the crash of Delta 191, the Federal Aviation Administration races to develop technology that can prevent microbursts from killing again.
If there is one crash that we can look back on now and say, this made things safer because we learned from it, it was Delta 191.
Okay. Okay, lights please. Pretty bad, right? Yeah. Here's the actual definitions for you to write down, but microbursts are the most severe type of low-level wind shear that you can encounter. It's a column of descending air that can get up to produce downdrafts up to 6,000 feet per minute, which is a lot. So a headwind loss of 30 to 90 knots is unrecoverable for a plane like us in the sling. For a jet, you saw it's almost unrecoverable in their instance as well. So produces strong turbulence, hazardous wind, direction changes, obviously, but it's a column of descending air, like has a cloud base right here that's talking about. So it's associated with convective precipitation into dry air at the cloud base. It can be indicated by intense rain shaft at the surface, but a cloud base and opening, like a ring of blowing dust, is the only visible clue. They're still working on ways to predict microbursts. Let's see if we can find the picture.
Did you say convective precipitation converted to dry air?
What it says on here.
Oh, yeah. Convective.
Yeah, into dry air. So let's. I want a real picture. There you go. See a column of descending air. Looks kind of crazy. So prediction for microbursts, I'm not aware of that has gotten any better for being able to predict it, but just visually, would you fly towards that? No. Right? So yeah. Hard to predict that it's going to occur in the area, but easy to avoid if you're able to see it from a distance like this. Descending column of air. The other one looks pretty centralized into a column. That doesn't look like a real picture. It's a real. I don't have a lot of real examples. Seems like this is the best one they have, but it's easy to see from a distance. So obviously if you're seeing descending air like that, you're going to avoid that area. I haven't heard of anyone here seeing a microburst in the area. I think it's pretty rare, but I don't actually know. So it's
Weather's like,
dry air. Convective precipitation into dry air at the cloud base. So it's going to be nothing happening around it, and then from the clouds creating precipitation, there's going to be like a suction of a column of descending air that comes out of that cloud base. But around it should be relatively smooth air. Okay, relatively common. I've never seen one, but that's what AI says. 10 microbursts reports for every 1 tornado. Okay, so the convective activity around it is like a tornado. We don't get a lot of, if any, does California get tornado? I didn't think so. I'm not from California, so yeah. Yeah, exactly. Earthquakes are happening around here, so more towards the plains, where tornadoes are occurring. It seems like microbursts are relatively common around convective activity like that, but I don't think they're particularly common in areas like California. I moved here from North Carolina. Mhm. Um, Reddit says microbursts are extremely rare, so I don't know what the answer is. I would guess not that common because you don't hear about them especially a lot. And I don't think the amount of accidents from a microburst has a lot of reported. I'm gonna look up that too, but I don't think there's a lot of reported. Not the 80s. It looks like the last commercial accident that happened because of microburst was in 1994, so it's been a while. Yeah, microburst detection systems like Doppler radar has provided like better information for pilots to avoid them, but like predicting the creation of microbursts doesn't seem like there's a lot of information or advancement in that, but being able to detect it so that other pilots can get away from it, and then training on how to escape and what kind of input you need to try to stabilize the aircraft during a microburst. We'll talk about that too. So I think we covered all this, yeah. Main thing you want to write down is a descending column of air that can produce downdrafts up to 6,000 feet per minute. And it can last from 5 to 15 minutes, which is a pretty long time. 15 minutes in the air. Okay, this picture is how they've increased knowledge about how to get out of a microburst or how to stabilize yourself to give yourself the best chance of surviving a microburst. So they figured out that the strong downdraft is obviously creating an int first if you're coming left to right into the microburst, like flying through the bottom of it. And your intended path they have right there is the green path. It shows you taking off a runway and you're taking off right into a microburst, which is probably stupid to begin with, but if you were underneath, the first part that you would hit of the microburst would increase your headwind, so it would slow you way down as you're entering the microburst. And then right in the middle of the microburst is like the strongest downdrafts that are pushing you towards the ground. So you're slow and you're being push to the ground, loss of altitude. Then on the outflow of the microburst, it's creating an increased tailwind that's pushing you out the other side of the microburst. Okay. So managing your speed, if you do happen to be trying to fly through the bottom of a microburst, is important, knowing that you're going to have an increased headwind here that's slowing you down, and then you're going to have an increased tailwind that's speeding you up on the other side. That's what we want to know. Okay, inversion. I already talked about this a little bit. It's an anomaly that can occur. It actually occurs a lot here. I've experienced it many times flying, but we just talked about temperature decreases normally as we increase in altitude. So when the temperature rises with altitude, it's called a temperature inversion. So it usually has shallow layers of smooth, stable air close to the ground. So it doesn't create turbulent conditions. It creates actually smooth, stable air. But at a certain point, it gets to the top of the inversion, and that kind of acts like a lid, keeping all the weather below it. The inversion, the top of the temperature inversion, acts like a lid. So if the relative humidity is high, meaning there's moisture in the air, it can contribute to the formation of clouds and fog and haze and all that. Okay. Main thing we need to know is temperature inversion is when temperature increases with altitude and it creates smooth, stable air close to the ground, but it only increases up to a certain point. So you have the top of the inversion, and that's kind of like a cap on the weather that's underneath. So if there's moisture in the air, it can create clouds and fog that is staying in that area, not moving, so it can decrease visibility. Does that make sense? Kind of keeping all of the clouds and fog or haze or whatever it creates capped at a lower altitude, wherever the inversion is, and that can create low visibility in the area. Okay. From that, we can get to relative humidity. So we already touched on this a little bit, but it's water vapor present in the atmosphere at any given time. So relative humidity is the amount of moisture in the air compared to the total amount of moisture the air can hold at that temperature, right? So they have a little picture of the molecules inside of a cup. 10% relative humidity versus 90% relative humidity. So relative humidity specifically is the actual amount of moisture in the air compared to how much moisture the temperature could hold. So they have an example. If the current relative humidity is 65%, the air is holding 65% of the total moisture that it's capable of holding at that specific temperature and pressure. Does that make sense? It's like a cup. That's why they have the cup here. The cup can only hold so much at a certain temperature and pressure, and then the percentage they give you of humidity is how much of it it's actually holding based on the temperature and the pressure. So relative humidity of 65% is 65% of the total moisture that the cup can hold. Okay. Then we get to determining cloud bases. Okay. So when this is getting a little bit far to go back to relative humidity real quick. So in the ADIS that we listen to, it gives us the temperature and the dew point, right? Yes, yes. So does anyone know what the dew point refers to? Anyone study? Yeah.
I mean, I don't know the definition of dew point, but I know that if the temperature and dew point are closer together, the air is more saturated.
Yeah, so the dew point is that saturation, that fully saturated air. So the temperature at which air must be cooled for it to become saturated with water vapor at 100%, right? So if you have, let's go back to this. So that's what they're talking about is the temperature at the surface is, wait, go back to this. There. The temperature at the surface is 85 degrees Fahrenheit and the dew point is 71 degrees Fahrenheit. So the spread that they're talking about is that temperature dew point spread, the difference between the outside air temperature and the dew point. Is that understood? Because they started talking about spread and we haven't even talked about what a temperature dew point spread is. Yeah.
Spread.
They give us both the numbers and then you can determine the spread, the difference between the two numbers. And the difference tells you how how humid the air is, how much moisture is in the air. So if we divide the temperature and dew point spread by the convergence rate, this 4.4 is always going to be the same. So if you have to determine a cloud base, first you find the temperature dew point spread. You find the difference between the temperature and the dew point. Then you figure out if you want to use Fahrenheit or Celsius. Fahrenheit, the number is going to be 4.4. Celsius, the number is going to be 2.5. So figure out if you're staying with Celsius or using Fahrenheit. Depending on that, you divide the temperature dew point spread by that number. So they used Fahrenheit up at the top. The spread is 14 degrees Fahrenheit. So you'd use 4.4. So 14 divided by 4.4, and then you multiply that by 1,000. Does that make sense? First, you find the spread but that's the difference between the dew point and the outside air temperature. In this case, it's 85 and 71 degrees Fahrenheit, so the difference between that is 14 degrees. We're using Fahrenheit, so we use the standard convergence rate of 4.4 degrees Fahrenheit. And we divide 14, our spread, by 4.4. Now, if you're getting the temperature and dew point in Celsius, which is more likely, they are giving you Celsius than Fahrenheit. If you're getting the temperature and dew point spread in Celsius, you would divide by 2.5, okay? 4.4 is what you divide if you're doing Fahrenheit, 2.5 is what you divide by if you're in Celsius. Then you multiply whatever that number is by 1,000, and you've gotten the approximate height of the cloud base for that area. So in this case, you've ended up with 3,180 feet, and it's always going to be AGL, above ground level. Cloud bases and cloud layers and cloud ceilings are all always given to you in AGL. Same with, they're talking about, or just look at the METAR. The METAR gives you the ceiling, which is the highest layer or the lowest layer of clouds. And that ceiling is given to you in AGL, not MSL. So if it's given to you in AGL and you want to figure out where it is in MSL when you're flying, what do you do?
At the airport.
Yes, add the airport elevation. That's how you get MSL. Okay? Are we following? Everyone looks really tired and over it, and I get it, but the more that we can get through today, the more review and actual practice we can do by the end of this. Okay. Actually, I don't even think it's on here, but how many people know how to read a METAR? Sort of. Have you practiced in King School? Let's finish up class today by looking at a METAR and how to read it. And then we'll start with fog tomorrow, because that's a whole nother thing if we gotta get into fog. So let's start with, it's easy to read on ForeFlight because it decodes it for you and tells you exactly what it's saying, but I'm sure you all have seen that That's not what you have to know how to read from. Okay. Okay, first, what is a METAR? Not necessarily, you don't have to tell me what the abbreviation stands for, because I can't even remember what the abbreviation stands for. But what information is it telling you? Anyone? Airport weather, good. Airport weather when? For the hour, perfect. Airport weather or the hour is what we need to know. Technically, it's 55 minutes, I believe, is there every 55 minutes they're supposed to update it, but it's airport weather for the hour is your METAR. Do we know what a TAF is? The winds, not the winds. It's a different type of. We haven't gotten to TAFs in the King School. We don't remember. Forecast. It's a forecast. Yeah. We can get back to this. We'll start with METAR. Okay. METAR. I'm sure you all have looked in ForeFlight. First of all, just go there. ForeFlight, you go to airports. I'm looking at Livermore Municipal because I did a sim this morning where we did a departure out of Livermore Municipal. So I go to weather. Oh, look, it's marginal. Marginal VFR. Do we remember what marginal VFR is? Yeah. Do you remember the specifications for what counts as marginal versus? Anyone wrote it down from last time? Nobody? What are the limitations of marginal VFR? What does that mean? Yes, that's the visibility. What about the? Thank you. Yeah. So for marginal, 3 to 5 statute miles visibility, and then 1,000 to 3,000 for the ceiling, meaning the cloud base. So we see the visibility is 10 statute miles, so the visibility is good, but the clouds are broken at 1,600. That's between 1,000 and 3,000. That's why we have marginal VFR being reported. But up here, so we have, it gives us like everything that it reads, but it has the actual METAR on the top. That's all the numbers and symbols and letters on the top. That's what it's telling us. So this is what we have to learn how to read. Up here, I can't zoom or point at it, but up here at the top, this is what we have to learn how to read without all this other information being spelled out for us. We have to learn how to read this. Okay. I'll go back to what's Torrance right now. Okay, there's Torrance. Firstly, it says METAR and then it has the airport ID, EB, right? Then it has the time. This was reported in Zulu time. Okay. And the first two numbers are going to be the date, and then the last four in the Zulu is the actual time. So today's the 8th, right? Yes. Today's the 8th of the month, so 08 for the day of the month, and then 1647 Zulu is the time that this was reported. Okay? First two numbers are the day of the month. Last four and the Z is the time in Zulu. Then does anyone know what this next part that starts this part? Wind direction speed. Good. What does that read then? Yeah, wind from 270, speed is 6 knots. Do we see that? Okay. What's the next part? Mean visibility. So this is 10 statute miles. Good. Next, what is this telling us? Clouds. Good. The ceiling. So what is this telling us? Yes, not 10,000, few at 1,000. Okay, 10,000 would be if it said 100, that would be 10,000. This is few clouds at 1,000. And then what are these two numbers? Temperature and dew point. And then how do we find the temperature and dew point spread? Subtract the difference, right? I don't know that off the top of my head. Then lastly, what is this? The altimeter setting for the hour, right? This changes hourly. It could stay the same, but it's updated hourly for the altimeter setting. So this is like the most standard that it could be, right? Is everyone following the basics? Okay, the time or the day and the time, the wind direction and the velocity, the visibility, the cloud ceiling, the temperature and the dew point, and the altimeter. Okay, let's look at. Okay. Does everyone know what speci means?
Special.
Yes, special weather report. So this means this is another update that they've given you outside of the hour. So they update this hourly, and if something changes significantly, they will update it in the middle of the hour, and that will be notified by a speci. A special weather report, something needed updating, so they released it between the hour. So there's the airport identifier. This, I think, is Watsonville, up north, and then the day is the 8th, obviously. The time is 1713 Zulu. Does anyone know what auto means? Yes, means it's given by automated weather service, so like an AWOS or an ASOS. What's the wind direction and speed? Thank you. Very good. That's the same statute mile visibility, so we know that. What does OBC mean? What is this telling us? Overcast at what? Overcast at 600. Good. Temperature and dew point spread. What's the spread here? 1, right? That's pretty close. So what should we expect? Moisture in the air means we can expect clouds and fog. Okay. And we know that's the altimeter. Do we know what RMK means? It means remarks. So it means there's something else afterward that they want you to know. This one gets everyone. Do we know what A02 means? Does anyone do any special research on? There's also, you can look up a legend for the METAR that has all of the different codes that could be on there. So look through a legend because it's gonna have information on stuff that we don't see ever in the area, like blowing snow. We never get snow here. So there's a code that tells you that there's snow, that there's ice, tornadoes, hurricanes. There's a bunch of different codes that can be added there. So look through there. Also important to know, if you don't know, if you're asked to read like a weird METAR on the northeast side of the country, and it has a bunch of not symbols, it has a bunch of codes that you've never seen before, you are allowed, 1, I would try to figure it out in front of them to show that you're trying to figure it out. But 2, if you literally have no idea, look up the legend. You can look it up in front of them. It's a source of information. Have the legend saved somewhere. Pull up the legend and just look at it to figure out what it means. But A02 has to do with the precipitation monitoring at the station. So this A02 means that at the airport, they have a monitor for precipitation in the area. That's all it means. That'll be like the trick question that they try to ask you in the phase check or something about what A02 means. It's just an indicator that they're able to look at precipitation in the area. Let's see if we'll come up with a legend. Were you able to just Google and find a legend on here? Okay, yeah, indicates the weather station has an automated precipitation sensor. That's all it means. Meaning it can differentiate between rain, hail, and snow. Make sense? Okay. That is probably, there's also stuff like this. Well, that you can look at that has different stuff to look at for all the weird remarks is gonna be what gets people at the end, but it's really, really common to see A02 or AO2 at the end of the remarks. Just tell them it means that there's an automated precipitation sensor that's able to differentiate between rain and snow and stuff like that. Okay? That's it for today. I'm done as well. This is way too much for today.